Operating a video platform at a global scale imposes immediate, crushing physical consequences. Software engineering is usually concerned with traffic and request rates. Video engineering is a fight against physical data weight. This typographic breakdown illustrates the baseline constraints for a modern Tier 1 streaming platform. We must support 5 million daily active users, requesting 5 billion views every 24 hours, while simultaneously ingesting 150 terabytes of new storage daily. This creates a severe read-write asymmetry. The system must ingest massive petabyte-scale binary large objects, or blobs, while simultaneously returning highly personalized, ultra-low latency reads to viewers around the world. As the schematic shows, a traditional monolithic architecture fails immediately under these conditions. If you proxy a 1 gigabyte file through an API server, that upload ties up a worker thread for several minutes. Scale that up and the server saturates, exhausts its memory, and crashes. The solution relies on a strict architectural divide. We must separate the control plane, which handles metadata and authorization, from the data plane, which carries the actual video bytes. Surviving internet-scale video requires moving away from single files and vertical hardware limits. Video data must be dismantled into parallel, asynchronous microevents. We begin at the ingest layer. The architecture requires 3 starting points: the client, the API gateway, and a dedicated authentication microservice. The gateway operates as the sole entry point, routing traffic and coordinating with auth to verify identity. To protect the gateway from spikes, we use a 3-tier rate-limiting architecture. Local clients report counts to zone aggregators, which feed a global controller. Using Redis, the controller calculates optimal drop ratios and pushes limits down to local proxies, avoiding centralized bottlenecks. With the gateway secured, a user can initiate an upload, but the actual video payload must never traverse this gateway. We use a pre-signed URL sequence. The client requests permission, receiving a cryptographic URL to push the video directly into S3 storage, bypassing the API. For reliability, the client breaks the large video into parallel chunked multi-part uploads, ensuring resumability if interrupted. By offloading the raw byte transfer to edge storage and utilizing chunking, the application servers avoid worker thread exhaustion and remain highly available. Once raw chunks land in S3, the bucket fires an event into a Kafka distributed commit log, decoupling ingestion from processing. This triggers a directed acyclic graph scheduler, which splits the file into parallel streams for audio extraction, thumbnail generation, and video encoding. To maximize compression efficiency, the encoder analyzes frames and slices the chunks exactly at scene changes, grouping visually similar frames to improve final output quality. Parallel workers then take these customized chunks and encode them simultaneously into multiple resolutions and different codec formats. Metadata requires a relational database, but heavy write pressure causes severe replication lag in monolithic MySQL. To eliminate this, we implement Vitess. Queries hit a VT-gate proxy, automatically routing across horizontally sharded VT tablet nodes, entirely abstracting sharding complexity from the application. Once processing completes, highly requested encoded chunks are moved to hot S3 standard storage. The massive original raw uploads are aggressively migrated to cold Glacier storage to minimize infrastructure costs. Combining an asynchronous compute pipeline and a sharded database ensures that ingesting petabytes of new uploads never degrades latency for users actively browsing. When a user opens the application, the system has a latency budget of a few milliseconds to query the database and populate a highly personalized home feed. Our recommendation architecture uses a 2-stage funnel. First, candidate generation evaluates watch history, distilling millions of videos into 200 relevant options. Second, the ranking model scores those candidates on freshness and predicted watch time to dictate the absolute final interface order. For explicit user searches, metadata is continuously indexed into a distributed Elasticsearch cluster, known as thundering herds. The system caches hot metadata and pre-rendered user feeds in memory using large-scale Redis clusters. Pre-computing recommendations and caching data guarantees instant discovery speeds, regardless of how large the total video catalog grows. Instead of routing to a central server, playback requests connect directly to an edge CDN inside the user's local ISP. To optimize storage, we package videos using CMath, wrapping both HLS and Dash protocols around a single fragmented MP4 file, halving edge costs. The actual delivery relies on adaptive bitrate streaming. It is streamed over HTTP in discrete, multi-second segments. This line graph plots the final piece of the equation, the client's local processing. The application constantly monitors network bandwidth. If a connection degrades, the client dynamically requests a lower resolution chunk from the manifest to prevent playback buffering. If a specific edge node fails to circ the chunk, the system registers a cache miss. A content miss means the video isn't stored locally, while a health miss indicates the server is overloaded. When miss rates climb, circuit breakers dynamically shed the client load, securely rerouting traffic to the next closest healthy CDN without collapsing the origin server, pushing content deep into local ISP networks and empowering the client device to adapt its streaming bitrate on the fly, effectively eliminates perceived network latency. When we assemble these discrete flows into this master architecture, the complete system relies entirely on specific engineering trade-offs. The most critical structural decision is prioritizing eventual consistency over strong consistency. Data synchronizes across regions with intentional, slight delays. It is completely acceptable if a viral video's view count takes a few seconds to update across different geographic zones. It is unacceptable if the video itself fails to load. We see the same logic in storage versus compute. The architecture intentionally burns petabytes of physical storage to hold dozens of pre-transcoded files, rather than attempting the computationally impossible task of transcoding video files on the fly. Operating at global scale relies entirely on precise orchestration. It is achieved by decoupling control logic from data transfer, dismantling monolithic files into parallelizable chunks, and pushing the resulting bytes to the absolute edges of the network.